Hi, and welcome back to Mr. Carroll's Classroom. Today we're going to talk about modeling with exponential functions. So let's go ahead and take a look. Okay, so first we're going to take a look and see why the exponential function y is equal to a times b to the x is actually really good for modeling any type of real life situation in which it follows an exponential pattern. So first of all, let's just to try to discover the nature of this, let's go ahead and set up an XY table. And we're going to just kind of look and see what's going to happen here. So if x starts at 0, then what do we end up with? Well, the y value is going to be a times b to the 0th power. And anything to the 0 power we know is 1. So that means that if I plug in an x value of 0, then I just get a back, which is actually really important. And we're going to see why in a second. Now, as x moves on to 1, then I have, of course, a times b to the first power, which is a times b. And I just want you to notice that this value happens to have the previous value in it. In fact, it has a in it, and then we're going to multiply by this value b, this factor we call it. There are many names for b, actually. And if I plug in, go up again for 2 for x, then I get a times b squared, which of course is a times b, which again you're noticing that the previous value is built into this. I have a times b, which is the previous value, times another b. And if I continue on, x is 3, then I have a times b cubed, which is a times b times b times b, which is again has that previous value, right? That x value of 2 of a times b, and then just again multiplied by another b. So what real world situations can we model with this? Well, any time that we're continuously multiplying by a common rate, or we would call it a growth rate or a growth factor, or there are actually a lot of different, it could be decreasing rate of decay, or decay factor. There are a lot of names for this b value. Ultimately, it stands for the base, but in real world situations, it's almost always some kind of rate that we are changing by, okay? Also, if we take a look at the a value, what did we start with? Well, when x was 0, and many times x actually stands for time, so I'm just going to use that in this case because it's easy to understand. So at time 0, we just get a back. So in other words, a can stand for your starting amount. Whatever you started with, that is going to be the a value. It could be the amount that you invested in a bank. It could be a population at a certain point in time. It could be, I don't know. Later we'll do the height of the bouncing ball. But either way, it's going to be that starting value is going to be a. Why does that work? Because when x is 0, or the time is 0, or that initial time, we just end up with getting a back, because b to the 0, doesn't matter what that rate or that factor is, b to the 0 is 1. Okay, which means that b, of course, as we know, is going to be our rate or our factor. Okay, and we're going to have to decipher our problems here to figure out what that rate or factor is. And then also, x is going to essentially be the number of times that we're going to multiply by that rate or factor. And many times, like I said, that it usually corresponds to time. Okay, so let's go ahead and see this in some examples. All right, so here's my first example. The peak height of a ball bouncing can be modeled by an exponential equation. And I want to just iterate here that it is just the peak height. Obviously, a ball bouncing is going to bounce like something like this, but we're just concerned with the peak height as it kind of goes down, okay? Unless it's a super ball or something like that, right? It's going to be a little bit less the height every time it bounces back up. All right, so anyways, so the peak height of a ball bouncing can be modeled by an exponential equation. The ball starts at a height of 5 feet, and its peak height decreases by 40% with each subsequent bounce. What is the peak height of the ball on its seventh bounce? Now, finding the peak height of the ball in the seventh bounce, that is going to be like the end factor here. First, we need to figure out an actual function or equation or an exponential function that is going to model this particular situation. So let's break this down. First of all, what are the important pieces of information? Well, it starts at a height of 5 feet. That's going to be our initial factor there, our initial value. Also, it says that it decreases by 40%. So what does that mean our rate is going to be every single time? What are we going to multiply by every single time? All right, so let's just remind ourselves. We're going to use, obviously, y is equal to a times b to the x, where a is going to stand for the starting point, and b is going to stand for the rate. Now, a is going to be that 5 feet. That's our initial starting point, our initial starting value. All right, at time is 0 in this case. And B is going to be 60%. Now, how did we get that 60%? All right, 60%, it's saying that it decreases by 40%. Now, if it bounced and it was the same every single time, it would be 100%, right? Every time it bounced back 100% of where it started, 100%, 100%, 100%, right? But in this case, it's saying no, it's actually going down and then it's decreasing by 40%. And so 100% minus 40%, if it's decreasing by 40%, then that means every time it's going to be 60% of whatever it was before. So that means our rate is going to be 60%. However, we never, ever, ever put in a percentage for our rate. We always convert it to a decimal, and 60% converts to 0.6. Okay, and the way you can do that is you can move the decimal to the left 2 places. All right, so now that we have our a value and our rate, our b, which again, b technically generically stands for base, but in almost all these problems it's going to stand for a rate. But anyways, let's go ahead and apply that to our function. And so again, I'm actually using y is equal to a times b to the x, but notice I gave this a name. All right, I called it h for height. All right, because that's kind of what we're getting back. Instead of x, I'm using t because t is representing time in this case. And yeah, so it's equal to a, which is 5, times, I typically use parentheses here. It just makes it look a little bit more clean. Times 0.6 to the power of t. And so now we're prepared. We've modeled this situation, and we can actually answer any question at any point in time. What would the peak height be for that given bounce? So in this case, on the 7th bounce, if we go ahead and we're going to plug in 7 for t, so 5 times 0.6 to the 7th power, and we get back 0.14. In this case, the units are feet. All right, so that's the height on the 7th bounce. All right, let's go ahead and do another one. So here's the situation here. You start investing, or you start a savings account with your bank, whatever bank you have, and the account has a 0.05% annual interest rate. Now, usually when I make these problems, I just put in like 3%, 5%. But actually, this time I did look up the actual average savings account interest rate, annual interest rate, for January of 2021. That's this month, this current month. And the average is 0.05%. Now, I will say this, the highest rate that if you went looking, it said was 0.5%, and the lowest seemed to be 0.01%. So you could, adjust this to be 0.5%, but honestly, it actually doesn't change that much. So anyways, if you just go to your bank account, odds are a 0.05% rate is what they're going to give you. All right. Now, if you initially deposit $1,000 and never touch the account, how much will be in your account after 30 years? All right, so let's go ahead and try to model this or create some kind of exponential function to model this. So first of all, the important pieces of information here are 0.05% annual interest rate and the initial deposit, initial value of $1,000. So we're going to go ahead and obviously A is going to be 1,000, but the interest rate, this one's a little bit harder because it's just such a small decimal value. So let's cover this really quickly. All right, so the rate is going to be, the interest rate, annual interest rate, is going to be 0.05%, which means that and that's a growth rate, by the way. It is going up by that. So we have to take 100%, right? And then add that 0.05%. If it was decreasing, then we would subtract like we did in the previous problem. But in this case, it is growing. So we are adding that 0.05%. So when we do that, we get 100.05%. And now I'm going to go ahead and convert this into a regular number. And so I'm going to move this decimal place over twice. So I get 1.0005. And that is our actual growth rates. All right, so now let's go ahead and apply these. So that means that, and in this case I said A of t, just stands for amount, I guess, in this case. So amount in a given amount of time is equal to my initial value at time is 0, right, of $1,000, and then times our growth rate here, our interest rate, which is 1.0005, all to the t power. So we're all ready to see if you invested today $1,000 and you never touched it, never even touched it, right? In that for that savings account, what would you end up with after 30 years? Well, we'll plug in 30 for the power, that for t, for that exponent. And what do we get after 30 years? Ooh, not so good, right? That's the state of savings accounts these days. Actually, it's been like that for a while now. But anyway, we would only end up with our initial $1,000 plus $15.11. So yeah. Anyways, and actually, if you did change this to 0.5, I did calculate that earlier just to see what the difference was, and it was somewhere around $1,161, something like that. So really, over 30 years, 161 bucks. Not too good. So what does that say? Savings accounts are really good for keeping your money safe, but not so good as an investment. So anyways, okay. So those are two real world situations and two real world examples. In one of those, we had a growth rate or a rate that was above 1, making our initial value go up and up and up. And the other one, the bouncing ball, we had a rate that was below 1, and so that made it go down, down, down. Okay. All right. So let's see here. The last thing I want to talk about are a few different derivations of this function and some terminology. So of course, we're starting with this basic simple y is equal to a times b to the x. And of course, we know that a stands for the starting value, and b is going to stand for our rate. But there's a lot of different ways to express the rate, and you're going to see a lot of different words being used, and here are some of the most common ones. Okay, so in a problem, in any type of real world problem, if you ever see the word decreases by, or is decreasing, or decays, or is decaying at a rate of, or depreciates, or half-life, that is indicative that this is going down. The rate is going down, which means that the rate should be between 0 and 1, okay? Some kind of fraction between 0 and 1. In this case, you can calculate that rate by taking 1, which is that 100%, minus the amount that it's decreasing by, decaying by, depreciating by, or if it's half-life, it's a little bit different. It just means it's the rate is 0.5. But anyways, you'll see those with the uses in like bacteria examples and stuff like that. What kind of terminology do you see for increasing? Well, of course, if you see increases, or is increasing by, or is growing or grows at a rate of, appreciates, yes, appreciates is the opposite of depreciates. Appreciates means it's going up. And then doubles would be like the opposite of half-life. But of course, you could have triples and quadruples and that kind of thing. In that case, we're basically going to take that rate and we're going to add it to 1. Okay. Again, 100% plus whatever that rate is converted to a decimal. All right, another thing that we're going to see, and we're actually going to explore this quite a bit in the upcoming lessons, is this is used extensively in finance. Okay, these exponential functions. In fact, it's used so extensively that they have broken down this very simple equation here into other kind of like subcategories depending on the situation. All right, so let's, of course, start with y is equal to a times b to the x, and I'm going to show you some of the most common um, financial formulas. Okay, so first of all, we have, this is called the simple interest formula, but we have a is equal to p times 1 plus or minus r all to the t. These are actually identical equations. These are absolutely 100% identical. The only difference is that they're using more explicit variables as far as the naming goes. A stands for that final amount, which is really just our y value. P stands for the principal amount, which is a financial word for your initial amount, all right? The amount you're investing or whatever, that's called your principal, but that is literally just the A. 1 plus or minus r is the same thing as b, your base. That's just your rates. And the only reason why they have plus or minus is because they're saying, well, if it's growing, then you should use the plus, and if it's decreasing, you should use the minus. That's it, okay? But other than that, it's literally the exact same thing as the b. And then, of course, in the finance world, we don't have an x, we have t for time, okay? But literally, these are identical. They're just using different names for the variables, all right? Now, if we expand on this a little bit, we'll get the compounding interest formula, which basically means, like, normally for the simple interest, this t stands for the amount of years typically, and with compounding interest, you can actually take an interest rate and then break it up over a smaller period of time. Like, say for example, you have an interest rate of 1, and they said, oh, but it's going to be compounded quarterly, so 4 times per year or every 3 months. Then that 1% interest rate is actually going to get divided into 4. So 1 divided by 4 is 0.25. So you'll have that 0.25% interest rate. And instead of t being every year, well, it's 4 times 1. So it's just 4 times. So literally, it's actually the exact same thing, except they're manually building in the division of that rate, essentially, okay, being multiplied over more periods of time, okay. And again, we'll have a separate lesson that is going to cover this explicitly with examples. And then finally, we have this other one, which is really derived from the compounding interest. This is it's commonly called PERT, because it's a is equal to p times e to the rt. And this is actually derived from the previous one that we just covered. And this is if something is being compounded continuously, like at every instant in time, all right, meaning as n approaches infinity here, this is what you would end up with, which again, we will have a separate lesson covering this. But anyways, so there you go. Oh, and E, by the way, is Euler's constant, and it is something that is really important in mathematics. It's an irrational constant, same type of thing as pi, okay? So anyways, that's what that is. All right, so we will use all of those and cover those in detail in future lessons, okay? All right, so anyways, I hope you got something out of this for today. It was really just utilizing this simple formula and then converting or modeling real life situations using that simple formula. So hopefully you found it useful, and hopefully I see you in the next one. Take it easy.